Well, hello, human biology students. I'm having a little struggle here getting this recording. This is actually my third attempt, so hopefully I'll get it right this time. I'm trying to pick it up where I left off on Monday, and I'm guessing a bit, so roll with me if I'm not perfect. But we're going to start in your notes with this line. There are 92 naturally occurring elements. If you look back at that periodic table, you'll see a good deal more than 92. In fact, this one goes up to 118. I think it might even go higher than that now. Many of these are proposed or believed to exist but have not been discovered yet. So we're not really worried about those. We're really worried about the 92 elements that are naturally occurring in our world. Just 4 of them make up 90% of the human body. Carbon, nitrogen, oxygen, and hydrogen are the 4 that make up 90% of our bodies. And so if you look at the notes, you'll see those listed there. Carbon, hydrogen, nitrogen, and oxygen. But if you wanted to step it up a notch, well, let's go with 99.9% of the human body. If we look at that, we can see that the list gets a bit longer, as you might guess. We would go with magnesium, okay, and then we would go with well, the ones I talked about: carbon, hydrogen, oxygen. I'm going to diverge just a little bit here. I'll get nitrogen in there in just a second. I'm going to go with phosphorus, potassium, iodine. There's nitrogen, sulfur, calcium, sodium, and oops, back up a little bit. I'm going to add another one in here. Iron, sodium, and chlorine. Okay, that makes up 99% of the human body. You say that's a ridiculous list to have to remember. Well, one of the ways you can remember something like that is I drove my MG, it's a little English car, to Chopkins Cafe, like that, and had salt. That's just an example of how you could memorize or learn something in biology without, trying to make associations. You don't have to remember that. That's just for kicks and grins. All right, so organic versus inorganic. Boy, what's the difference there? You go to the grocery store and you see this, the organic section, grown without pesticides. That's actually not true. If you look at it, here's a list of approved organic pesticides, and you can see on it some of the things: various copper-based substances, boric acid, Bacillus thuringiensis, that's BT, like BT corn, BT soybeans, gibberellic acid, corn gluten. All these are approved organic pesticides, so that's not exactly true. But what distinguishes organic from inorganic? And largely, it's if this isn't true, well, it's what kind of fertilizer are they using? So most crops are grown with inorganic fertilizers like Miracle-Gro, and organic types of produce are grown with organic fertilizer like that, cow poop. Okay, if you look at where the others come from, well, it's natural gas, various rocks in the ground. That's where you get potassium from, and but organic uses cow poop. Okay, well, biologically, what are we looking at here? Well, organic simply is defined as those items that contain carbon, and inorganic contains no carbon. It's as simple as that. So when we start talking about organic and inorganic, that's what I want you to think about. If it contains carbon, it's considered organic. If it doesn't have carbon, it's inorganic. These are terms that will come up later as well. So this is just a brief introduction to them. An isotope is another important term. That's an atom with an unusual number of neutrons. Okay. Now, if you go back to the periodic table and we look at carbon here, and we see this number up here, which hopefully I've already talked about as the atomic number, and here's the atomic weight. If you don't see a plus or minus sign by that C, then you can assume that the number of protons, is the same as the number of electrons. If it were different, there would be a plus or a minus sign here, and there'll be more on that later. Okay, down here, this is the atomic mass. Okay, this is the weight of all the things that make up a carbon atom. And it's 12.011. Okay, well, Isotopes have an unusual number of neutrons. Okay, so if you've got 6 protons here, and you see an atomic mass of 12, well, then you can assume that you take 6 away from the 12, you're going to have 6 neutrons. But I've never seen 0.01, if you will, of a carbon atom. So where does that come from? Well, I'm guessing you've heard about radiometric dating. I'm guessing you've heard of carbon-14 dating. And carbon-14 dating, well, it comes from the fact that most carbons in all the world are carbon-12s. 6 protons, 6 neutrons makes 12. But occasionally you'll find a carbon with an additional neutron, that's carbon-13, but it's stable. Then even more rarely, like the foods that you eat at lunch or whatever, will have a carbon with 2 additional neutrons, and that will be carbon-14. If I grab this cow leg bone here, how would we tell how old this is? We might use carbon-14 dating. And so somebody would take a piece of this cow leg bone and they would analyze it, and they would try to figure out how much carbon-14 was in that piece of cow leg bone. And the idea is this: carbon-14 is unstable. It breaks down into nitrogen-14 over time. So if this cow was alive yesterday, there wouldn't be very much nitrogen-14 because the carbon-14 would be the predominant molecule in this leg bone. But after that animal died, after an amount of time, there would be more and more nitrogen-14 as time progressed. And so that would be a way that we would tell how old this leg bone is, by how much nitrogen-14 is in it compared to carbon-14. The more nitrogen-14, the older it is. The more carbon-14, the younger it is. Okay. So that may be something familiar to you. So the bottom line, though, is this. There's carbon. Most carbon in all the world is carbon-12. Some's carbon-13, some's carbon-14. So this right here is an average of all the carbons in all the world. So 12.011. That recognizes the fact that there's a little bit of carbon-13 out there, a little bit of carbon-14 out there, but most of it's carbon-12. And so the carbon-13 and the carbon-14 would be considered an isotope. An atom, a carbon atom with an unusual number of neutrons, and so just a little bit different. Okay, bonds are next. Okay, and so we talk about ways that atoms are joined together, and you know, I've got anabolism and catabolism here. I want you to more remember this principle right here. If you join 2 atoms together by creating a bond, you have used energy. It requires energy. You may also say that the energy is now stored in that bond, but it requires energy to make a bond, to bond 2 atoms together. Breaking a bond releases energy, and we call that catabolism, but releasing an energy. When you burn firewood, you are releasing bonds that hold carbon atoms together. That is the energy that we feel as heat. Okay, so let's see here. Yep, I'm where I want to be. Okay, so so we're going to consider some bonds, and the first 2 are ones that I'm pretty sure you're familiar with. Bond number 1 is an ionic bond. It's a bond between 2 atoms of opposite charge, and your textbook uses a fairly familiar picture, I think, and that's this one right here. And here we have a sodium atom, and here we have a chlorine atom. Okay, it is chlorine yet; it's not chloride yet, so chlorine. And when we look at this atom of sodium right here, if we go back to the periodic table just to reinforce, and we find a sodium right here, and there's 11 here, and you don't see a plus or a minus by that sodium, then you should assume that there's the same number of electrons as protons. If you had more electrons, there would be a minus sign here, because you now have an extra negative charge. If there were more protons, there would be a plus sign here because you would have more positive charges in that atom. Okay, so if we go back here, we see the sodium atom, and hopefully the first lecture I got to talk about the octet rule, how the atoms like to have 2 electrons in the first shell and 8 in the second shell. Here we have sodium with 1, 2 in the first shell, and then 1, 2, 3, 4, 5, 6, 7, 8 in the second shell, and then 1 in the third shell. So it's got a total of 11 electrons, but only 1 in that outer shell. Here we have chlorine, 2 in the first, 8 in the second, and 7 in the third shell. Now, atoms like to have a filled outer shell. And if you remember, the electrons in that outer shell are the highest energy. They like to fly off of there and do so fairly readily. And so, thinking about that, then this sodium atom is going to lose that electron pretty easily, and the chlorine will receive it. Now, when the sodium atom loses that electron, now there is one less electron out here than there is proton in here. I wish they had 11 little circles in here to represent the protons, but that's what would happen. And so we have a plus charge. There's more protons than electrons. Then here in the chlorine, since it got that electron, now it has one more electron than protons, and it has a negative charge. And just like people, opposites attract, and we have a salt molecule. And it does tend to have that cubic form. I have one right here. Hopefully you can focus on this. This is a large salt molecule, so not molecule, but large salt piece, and it has that square look to it, like you see in the little pictures here. And if you take your salt shaker and look at it closely, you'll see a similar thing there. Okay, so we would call that an ionic bond, because when these atoms develop a charge, they become an ion. Okay. A covalent bond is a little bit different type of a deal, a little bit different item. Okay, if we go here, we're going to use oxygen and hydrogen to talk about covalent bonds. I suppose I better go back and just look at the definition that I have here. Okay, a covalent bond, let me smooth this down a little bit so it's top of the page. A covalent bond is a bond formed when two atoms share one or more electrons. Now, real important difference here. In this one, in an ionic bond, an electron moves from one atom to another. It's no longer around the sodium, it's now around the chlorine. Okay? With a covalent bond, an electron is shared. That means it spends part of its time around one nucleus, part of its time around another. You got to keep that in mind. Shared versus taken or lost. In a covalent bond, it's shared. So here we have an oxygen atom with 2 in the first shell and 6 in the outer shell. And of course it wants 8, so it's looking for 2 more. And here we have hydrogen, which, look at this, it's really just a proton, 1p, with an electron around it. It doesn't even have a neutron, okay? But well, there it's got that electron. So rather than take it away, the oxygen shares it. And that's what we have over here. And since the oxygen wants 2 electrons, it's sharing the electron with 2 different hydrogen molecules. That's what we see over here. And so this hydrogen, this electron spends part of its time around that hydrogen atom and part of its time around that oxygen atom. Okay? And same with this one. Part of its time around the hydrogen atom, part of its time around the oxygen atom. Now, it's real important to notice here that the oxygen atom is larger than the hydrogen atom. So that electron that is shared spends more time traveling around the oxygen nucleus than around the hydrogen nucleus. Okay, keep that in mind. It's real important to the next item here. Okay, so again, ionic and covalent bonds, I'm suspecting those are fairly familiar to you. Okay, so the last one then is the hydrogen bond. So here, if we look back at those images that I had right here, because that electron spends more of its time here around this large oxygen atom and less of its time around this smaller hydrogen atom, that negative charge, remember electron has a negative charge, that negative charge is more often here and less often here. So that this side of the molecule, so the molecule is this whole thing, the 2 hydrogens and the oxygen is the molecule. That molecule will have a slight negative charge on this side where the electron spends more time, and a slight positive charge on this side where it spends less of its time. So if we look at another representation of that, that's what we see here. And here, this is an image from your textbook. Here you have a plus side on the hydrogen side and a negative sign on the oxygen side to represent that. Well, what's the significance of that, you might ask? Well, the significance is that It gives water an attraction. So the plus side of a water molecule is attracted to the negative side of another water molecule. And that is a hydrogen bond. It's a weak attraction, if you will, between two hydrogen molecules. And that, ladies and gentlemen, is what makes skin on water. Oops, that's not the one I want. You've already seen cow poop. Okay, we'll deal with this in lab next week. So that meniscus, we call that a meniscus. Here the water is crawling up the side of this glass tube. Glass is going to be what we call polar, and so water crawls up the side of it. And it's also what allows for insects to walk on water. They're walking on that skin of water, if you will, and has that sort of a look. Okay, we'll get to that in a second. Okay, so that's a hydrogen bond, and so there is this concept of polar versus nonpolar. So if we go back here, water is considered a polar substance because it has that plus and minus end to the molecule. So, let me go back to the other one here. Now this will do. So this side is minus, this side is plus. If there were no charge difference between the sides of the molecule, we would call it nonpolar. And that's things like oils, like we're trying to show here, where oil and water separate. I just happen to have a little olive oil here, so we'll see if this will work. If I can do this. There we go. In front of the camera. Ta-da. Okay, and that's because oil is nonpolar and water is polar. They separate. They form two different layers. And you may know this if you have enjoyed the lake this last summer, and you've used a boat or a jet ski or something, and you may have seen the gas forming that rainbow-like appearance on the top of the water. That's because the gasoline is nonpolar and it stays on top, floats on top of the water. Okay. All right. Getting towards the end of things here. So if we look at then the next item is acids and bases. And that olive oil container is kind of stinky. What do you do? I guess I rub it on my pants, right? Okay, so acids and bases are where we want to go next. So acids are any substance that releases or causes the release of hydrogen ions into solution. Okay, well that's a lot of words. Well, we know what an ion is. It's an atom with a charge. And I'm going to go down here because I want you to know this. But this is one equation. Here we have carbon dioxide, what you breathe out. Here's water, what you drink. So when those combine in your body, they form this. This is called carbonic acid, H2CO3. But H2CO3 is the most common naturally occurring acid, but it's a weak acid. It doesn't break down completely, and it breaks down very readily. And that's what this arrow is indicating right here, that this molecule, carbonic acid, is breaking down to this molecule. This is a very important molecule. It's called bicarbonate, HCO3, and also a hydrogen ion. So because this hydrogen ion is standing alone over here, and it's come from this molecule right here, we would call this molecule an acid. It has caused there to be more free hydrogen ions in a solution or in your body. Okay, so that's an acid. Some common acids. Well, common acids that you think of would be like sulfuric acid, nitric acid. You know, make a longer list. I thought I'd show you an example of a nasty acid if I've got it here. This is the come on back. I guess I'll there it is. Yeah, that's what I want. Okay, this is hydrofluoric acid. I had a student a few years back that worked with a lead in soils analysis, lake bottom sediment, and he had to dissolve the lake bottom sediment in hydrofluoric acid. And so it came in a plastic bottle. Well, that seemed innocuous enough. So he got the lake bottom sediment, put it in a hardened glass beaker, put it on a hot plate because it dissolves quicker if you heat it up, added the hydrofluoric acid. The hydrofluoric acid, if you think about it, its job is to dissolve lake bottom sediment. Well, a lot of lake bottom sediment is silica, it's sand. It's what glass is made of. And that's what the labware was made of. And so, but it came in a plastic bottle. How can that be bad? Well, pretty quick as he's heating it up, that hydrofluoric acid ate up the sediment real fine, but then it also ate right through the hardened glassware, went onto the hot plate surface, and poof, went up the vent hood. Kind of a scary stuff. If he got it on his fingers, this is a very mild hydrofluoric acid burn. But if he'd gotten some direct contact, it would have burned right through his skin, right through his bone, and gone out the other side no matter how much water he put on it, because water doesn't neutralize that particular type of acid. So there's some nasty stuff out there. I want you to think about, and maybe we'll talk about this on Friday, what foods do you consume that are acidic? And we'll also talk about foods that you consume that are basic. And we'll see if we can make a list with a point to it. Okay. So acids, yep, those are things that make a lot of hydrogen ions in solution. A base is something that makes a lot of hydroxide ions in solution. You know, and you think about it, if you know, bases get kind of a short straw. In movies, boy, the arch villain, if he falls into a vat of acid, it's a bad thing. If he falls into a vat of base, is it as big a deal? You know? Well, it should be. For example, this is a cabin my wife and I have built. And it's a log cabin. And when we were building it, I was scrubbing logs. And just on the inside, right about here one day, I had one last bit of log to scrub to clean off debris before we finished it, put the finish on the interior. And I was using bleach. And I was using rubber gloves. Well, my rubber gloves ripped. And I only had this one little piece, you know, it was just maybe 3 feet by 2 feet left on the wall to do. So I'm just going to barehand this. So I took my scrub brush, dipped it in the bleach, and started scrubbing the cabin wall. Did that for about 10 minutes, got her pretty well finished, and looked down at my fingertips, and they were bleeding. If any of you have ever gotten bleach on you, or feel it, it's kind of got a nice, smooth, soft feel to it, like soap suds, you know. Well, the reason it's got a nice, smooth, soft feeling to it is because the bleach is dissolving your top layer of skin into a nice, slippery slurry. And that's what I'd done to my fingers. And they started bleeding. I'd done such a good job of it. So bleach can be just as nasty as acid, but with the opposite pH. So pH is the scale that measures how acidic or basic something is. And it runs from 0 to 14. 0 to 6 is acidic, 7 neutral, 8 to 14 is basic. And your body really has to do a lot of work to try to keep that pH in the right range. And so it uses buffers to do that. You know, we'll talk about things that you consume that are acidic and basic. But common things that your body uses to buffer what you eat would be bicarbonate. That's that molecule right there that we talked about before. Generally, phosphates can be good buffers, and proteins can be good buffers. These are kind of generic terms, and that's okay. But just to make the case for how important this is, we're going to talk about the fact that really 90% of what you consume tends to be acidic. And we'll see if we can make that point with what you come up with on Friday. But your body has to maintain your internal pH between a pH of 7.35 and 7.45. That's your blood. Your blood has to be maintained in that range. And so if you drink a lot of pop and coffee, a lot of fruit juices, they might have pHs in the 4s and 5s, and you're just chugging that stuff right down. And your body is really quickly stuffing that into your blood. And so you've got to have a way to buffer that acid that you're consuming. And so if you can't, if the pH goes too low, which is a way of saying gets too acidic, okay, don't be confused by that. Low pH is acidic, then you get cramps, headache, confusion, convulsion, tremors, and if it goes long enough, you die. Well, let's say you're a big consumer of high pH foods. Well, then, and if your body can't effectively buffer them, then you get muscle twitch and tingle. You might faint. You might go into a coma. And again, you might die. So it's a big deal for you to be able to buffer what you eat. And so these acids and bases have to be buffered. Well, how do we do that? Well, if it's an acid, there's the acid that you've consumed. Maybe it's coffee or pop. We're just representing that with the hydrogen. And here's the buffer that your body would dump into the system to take care of that extra acid. Well, how does it do it? Well, it turns it into carbonic acid, and then pretty quickly it breaks it down into water, which you use in your body, and CO2, which you exhale. If it's a base you've eaten, your body would then take that base. It would combine it with with carbonic acid. Hydrochloric acid is the acid in your stomach, by the way. It would combine it with carbonic acid and turn it into water and bicarbonate, which will then use other places in your body to buffer any acid that you might have. So that's how an acid is buffered. That's how a base is buffered. And we'll pick it up on Friday. So hopefully that's any questions that you have, bring them to class on Friday, and I will try to answer them there. Otherwise, we'll start with organic molecules on Friday, which there are 4 types: proteins, carbs, lipids, and nucleic acids. I'm guessing 3 of those are quite familiar to you. And they all contain carbon and hydrogen, but carbon, which makes them organic. Okay? Thank you.